Alright, welcome back. In this lesson I'm going to describe how to do integration using the method of substitution. Method of substitution is necessary when we have more complicated looking integrals. For example, we'll pick on the bottom right one here, antiderivative of x times e to the 9x squared. We could play some games and try some stuff out, like maybe the answer, this is e to the just 9x squared plus c. But if we were to take the derivative of that, we would get e to the 9x squared multiplied by the derivative of 9x squared, because we have to use the chain rule, which would be 18x, not x. So we would need to correct for this by putting a 1 over 18 in front. And so on. We could indeed solve many integrals this way by proposing a solution and seeing how is it wrong, how is it off. Is it off by a constant? Can I compensate that by incorporating a constant? But in general, this is not a very safe strategy to use. There are some functions that you can't integrate by using this kind of a guessing method, this kind of random, not really random, but this uncontrolled approach. What we will be doing is, just like the previous antiderivatives we talked about, is we're looking for the mystery function whose derivative is equal to the thing that we're taking the antiderivative of. So d by dx of what gives us 4x plus 1 to the power of 9. When we get our final answer, what we will always be able to do is check it by taking its derivative and making sure that it matches the original thing inside the integral. So that's what I'm going to do here. Before we talk about the method of substitution, I want to just show you how you can always check your answer. Is it true that the antiderivative of 4x plus 1 all to the power of 9 is 1 over 40 times 4x plus 1 to the power of 10 plus c? If it's true, then it must be the case that this derivative of 1 over 40 times 4x plus 1 to the power of 10 plus c. After I do this derivative, it has to give me 4x plus 1 to the power of 9. If it doesn't, then this statement is incorrect. Okay, I'm going to rewrite this as d by dx of 1 over 40. Actually, I'm going to take the 1 over 40 out front, because you can do that for derivatives, right? Take the 1 over 40, take the constant out front of the derivative operation. I'm going to replace the 4x plus 1 with a w, plus the derivative of c. I'm going to split the derivative of the two components up. W is equal to 4x plus 1, not 10, 4x plus 1. Okay, now how do you take the derivative of w to the power of 10? You get 1 over 40 times 10 w to the 9 multiplied by w prime. The derivative of c is 0, since c is a constant. So we're going to need w prime. Derivative of 4x is 4. Derivative of 1 is 0, so we get a 4. So we have a 10 over 40, that's 1 over 4. W is 4x plus 1, power 9, and then w prime is a 4. The 4 on top cancels with the 4 on the bottom. And we get what we're supposed to get, 4x plus 1 to the power of 9, as needed. This only confirms that that's the answer. We didn't get the answer using this approach, we just confirmed that the answer is correct. So this is how to check your calculation. So we're going to learn the method of substitution in order to get that final expression with 1 over 40 from the initial expression that we're trying to take the antiderivative of. What we're doing inside these examples is we're actually running the chain rule backwards. Notice when we took the derivative of that answer, we had to use the chain rule. So we need a method for reversing the chain rule, for going backwards. As an intermediate step, we're going to do something called calculating a differential. We calculate the differential of different expressions. A differential isn't really new. It's taking the notation that we already have for derivatives, actually the two notations we have for derivatives, and putting them together. We know that the derivative of, let's say we have a function y equals f of x. We know that we can write the derivative operation as d by dx of the function. We also know that we can write the derivative operation with a prime, like f prime of x or y prime. Well, let's combine these notations. If we know that they're the same, if we know that dy by dx is the same thing as f prime of x, if y is equal to f of x, then we can cross multiply both sides by dx, and we get dy is equal to f prime of x times dx. This is its own mathematical object. dy tells us how much does the y variable change by, dx tells us how much does the x variable change by, and f prime of x tells us the rate of change of a function. So if we know that the x, let's say we know what f prime of x is, and we know how, we want to find out how much does the y value change in a certain region, we would take the derivative of the function, evaluate it at a point near that region, then multiply by how much of a change we want to make in the x direction. And that's going to be an approximation for how much the y value changes by, as long as, and the approximation will be good as long as we don't change the x variable by very much. We're not going to do any of that. We're not going to play with differentials and apply them to anything. We're just using them as a temporary thing in our calculation of an antiderivative. So I'll show you what I mean. Let's find the differential for this function y equals sine of x. So we start with the initial statement, just the usual statement of what a derivative is. The rate of change of the y variable with respect to the x variable can also be denoted by f prime of x. So dy by dx is equal to the derivative of sine of x, which is cosine of x. And now we can cross multiply. Cosine of x multiplied by dx. And that's it. That's our whole answer. We treat the dy by dx as a fraction and then isolate for the dy part. So we'll do another one. Find the differential for y equals e to the tan of x. So I'm going to start with our statement. Dy by dx is equal to f prime of x. So dy by dx. This expression here is an e to the power of w. So when we take the derivative of e to the power of w, we have e to the power of w times w prime. So dy by dx is equal to e to the tan of x multiplied by the derivative of tan of x, which is secant squared of x. And we're almost done. I'm just going to cross multiply by the dx. So dy is equal to e to the tan of x times secant squared of x times the dx. That's our answer there. So really, the only thing we're doing that we didn't do before so far is after we take the derivative, we just isolate for the dy part of the derivative. We are going to do something else though. We're also going to have a different type of rearranging game. Sometimes we're going to have, like when we're doing integration by substitution, like we'll see in a moment, we'll need to isolate for the dx. And we could have done that in those previous examples. So if we go back to that first one, I could say or dx is equal to, now let's divide both sides by cosine of x, dy over cosine of x. And for the second one, we could have or dx, now divide both sides by e to the tan of x times secant squared. So dy divided by e to the tan of x times secant squared of x. And that's what we'll be doing in the next examples. Is we've been given the derivative of w. We've been told that dw by dx, just like dy by dx, is equal to something. And In these examples, we want to isolate for the dx term. So I'm going to do that in a few steps. I'm going to begin by multiplying both sides by 7 and multiplying both sides by, or actually dividing both sides by 3. So 7, actually no, I'm a liar. I'm a big liar. I'm going to multiply both sides by 7. So 7 dw by dx is equal to 3. And then I'm going to cross multiply both sides by dx. So 7 dw is equal to 3 times dx. And then finally divide both sides by 3. And we get dx is equal to 7 dw all over 3. And yeah, that's a lot of steps. You wouldn't have to show all that if this was a show your work type of calculation. You could go immediately to that answer. But that's just showing that the only thing that we're really doing is we're multiplying and dividing both sides by the same thing in a particular order to isolate for one part of the expression. In the next example over on the right, we're going to do the same thing. This time I'm just going to multiply both sides by the dx term. So 2x e to the x squared times dx. And then I'm going to divide both sides by 2x e to the x squared in order to get dx all by itself. So dx is dw divided by 2x times e to the x to the 2. And that'd be our answer. Okay, next one, similar. I'm going to do 2 cross multiplication steps at once. Multiply the 2 on both sides. Multiply both sides by dx. So 3x to the 1/2 times dx. And then I'm going to divide both sides by 3x to the 1/2. So dx is equal to 2 dw divided by 3 times x to the power 1/2. And then the last one here, I'm also going to do it in a series of steps, but my first step is going to be a little bit different. I noticed that negative exponent can be rewritten as a positive exponent in the denominator. So dw by dx is equal to 1 over 2 multiplied by the root of x downstairs. Power 1/2 means square root, negative power means bring it down. Now I'm going to cross multiply. So 2 root x, oh, not 2d, 2 root x dw is equal to 1 times dx. And there's our answers. Mostly review of fractions, I guess. How to work with fractions, how to manipulate them and isolate for different parts of them, and how to isolate for the bottom of a fraction. Cross multiply, and cross divide. Okay, now we get to the business part. What are we doing with the substitution method? When we were taking derivatives, there is this intermediate step where I would let w equal some part of the expression. And we're going to do the same thing for antiderivatives that are more complicated, like this one. I'm going to let w equal the part of the expression that's plugged into some other part of the expression, like the part that's inside the function. Like if I was taking the derivative of this, what would I let w equal to? Well, I'm going to let w be equal to that thing for the antiderivative as well. So let w equal 3x. That's going to be our substitution. Then I'm going to rewrite this as 3 times the cosine of w, since I've replaced the 3x with a w, but I also need to replace the dx. So I'm going to take the derivative. dw by dx is equal to the derivative of 3x, which is 3. Cross multiply and cross divide, and get dx is equal to dw divided by 3. Put that here. The 3's are going to cancel. I have a 3 outside up there and a 3 down there. And I'm going to rewrite the question. Okay, so we've taken an antiderivative of the cosine of 3x with respect to x, and we've replaced it with an antiderivative of the cosine of w with respect to w. the fact that we have a w here instead of an x doesn't change the way that we take an antiderivative. So what do I take the derivative of with respect to w if I want to get cosine of w as the result? And the answer is sine of w. We would do the same thing we would do as if it was an x. Just like when we were taking partial derivatives. With x's and y's and z's, well, it's just a different letter of the alphabet. It follows the same rules as the other letters of the alphabet. Sine of w plus c. Now, we're going to do the same thing we also did in those derivative calculations. So I'll go back to that first example. After we got down to 1 over 40, 10 w to the 9 times w prime, I took the w prime and replaced it by what it was, and I took the w, and I didn't leave it as a w, I replaced it by 4x plus 1. So I'm going to do the same thing here. I have my answer, but my answer isn't ready. I'm going to put it back in terms of x. So is equal to the sine of 3x plus c. And I invite you, I'm not going to do this, I want you to do it, to check. You confirm that d by dx of the sine of 3x plus c is equal to 3 times the cos of 3x. Because that's what has to be true if this is the answer. Okay, another example. Now I want this antiderivative. 3x squared over the square root of x cubed plus 2. And this is what I mentioned about the guessing game. Try playing the guessing game for this one. What do I take the derivative of in order to get this? And it's not going to work out very well. Now I'm going to look at this expression and ask, is there some part of the expression that's being plugged into another part of the expression? Is there like a composite function aspect here? And there is. I have an x cubed plus 2 that's being plugged into a square root. I'm going to let that thing equal w. And a natural question is, well, what about the quotient rule? Do I need to undo the quotient rule? Maybe. But maybe we can get away with it, with not trying to right now. Maybe this function's special and we won't need an anti-quotient rule. Okay, so I'm going to let w equal x cubed plus 2 for the only reason being that that's the thing that's plugged into something. So I'm going to rewrite my integral. I have an x squared, 3x squared up there, and that's a problem. I'll tell you why in a moment. Then square root of w down here. And now I have to replace the dx with something. I have to put that dx to be in terms of the new variable. What we're doing in these types of substitution calculations is we're transforming the expression from one variable into another variable. And it is quite profound. Like, you know, you have your x-axis and you have your y-axis. Well, we're changing the x-axis to be a w-axis now. That's really, there's a lot of geometry that we could be interpreting a lot of these steps geometrically, and I'm gonna go back and do some of that later. But there is something philosophical happening when we do a substitution. Okay, so now I'm going to do the derivative of w with respect to x. I get 3x squared plus 0, then cross multiply and cross divide to get the dx all by itself. So dx is equal to dw divided by 3x squared. And something wonderful happens. We never ever want a mixed expression with two variables in it. We don't want to have w's and x's in the same antiderivative. That's a nightmare, and if that ever happens, that either means that we're stuck and we picked the wrong method, because there are multiple methods of taking an antiderivative, or it means there's something we have to do. There's some trick we have to do. There's some manipulation that we're going to have to follow through with in order to get the expression to be entirely transformed in terms of this new w variable. Fortunately, in this case, that doesn't happen, or nothing bad happens actually. We can cancel the x squared on the top with the x squared on the bottom. That gets rid of the entire old variable. The x is completely gone. We've rewritten the question 100% in terms of the new variable. So we have the antiderivative of 1 over the square, I'll go back to the normal colors. Antiderivative of 1 over the square root of w, dw. And maybe this doesn't look so hot, but remember, square roots are power 1/2, and a power in the denominator can be brought up to the numerator with a negative. So we have w to the negative 1/2 dw. And this is just like the antiderivative of x to the negative 1/2. We can use the anti-power rule. So anti-power rule. So the power increases by 1. So negative 1/2 plus 1 is positive 1/2. And we divide by the new power. So 1 over 1/2 w to the 1/2 plus c. Dividing by 1/2 is the same as multiplying by 2. So 2 w to the 1/2 plus c. And now we can undo the substitution. Undo substitution. So we have 2 times x cubed plus 2 to the 1/2 plus c, or even better, turn the power 1/2 into a square root, x cubed plus 2 plus c. And on your own, confirm that the derivative of this of 2 times the square root of x squared plus 2 plus c is equal to 3x squared over the square root of x cubed plus 2. Because that's what the claim is. The claim is that the derivative of that gives us what we were originally asked for the antiderivative of. There's many question types where the substitution that we need to use is not going to be clear. There might be 2 candidates. There might be, oh, I can do this or I can do that. Or there might be no candidates. There might not be anything there at all. I'll give you an example where there's nothing at all apparently to substitute, but substitution is still involved anyway. Antiderivative of tan of x. In order to do this integral, we have to use a trig identity. That's that tan of x is sine of x over cosine of x. And now we have 2 kind of choices. We could let w equal the top part of the expression or w equal the bottom part of the expression. And it turns out that both of them will work, but the best one, the one that most quickly and easily leads us to the solution, is let w equal cosine of x. And I'll let you finish. So pause the video and try that out on your own. Okay, and I've put the answer here and the steps. So make sure you can do a calculation like this. But the important weird thing here was there wasn't a clear choice. And it wasn't even clear that we needed to use that trig identity to rewrite tan of x in terms of sine and cosine. So I definitely don't want to give the impression that every time we do an antiderivative, it's going to be clear what it is that we have to do. You will make mistakes, and the mistakes aren't necessarily math errors. They could be strategy errors, and you just try a different strategy. You try again. So that's what that trial and error refers to. It refers to the fact that we are not taking derivatives anymore. There's not a concrete way you're supposed to go. There's a host of strategies that we have access to. Some of them work well, some of them don't work at all. And a lot of them are in the middle. They work, but it can be really nasty. Okay, let's do a more nasty looking one, but it's actually not that bad. I think, if I didn't screw something up. 3, 5, maybe it's screwed up. I may have to do a repair on this. So sometimes I make up a question and in my mind it works out so well, but in practice something's wrong with it. So we have 2 parts of this expression. We have one part that's inside a bracket to the power of 9, and we have one part that's inside a bracket without a power on it. It's really ugly. Looking at this, you wouldn't want to guess what the answer is. 1 over something times x cubed plus 5x to some power, like power 10, right? That would be a reasonable guess. But you don't want to like play around with numbers and, you know, what do I have to divide by and that type of thing. Using this method of substitution is more reliable, more consistent. So I'm going to let w, of the two choices, do I let w equal the thing that's raised to the power of 9, or do I let w equal the thing that's not raised to any power at all? Well, always choose, at least at first, something that is being raised to a power, or something that's, you know, part of the expression that's being plugged into something. So being plugged into power 9, that's the first thing to try. So I'm going to let w equal x cubed plus 5x. So then I'm going to rewrite our integral. Integral of w to the 9 times this bracketed term still there. And we're going to need it to disappear, or kind of disappear. And we're going to have a dx replacement. We need this dx replacement to be really nice. So dw by dx is equal to 3x squared plus 5. We rearrange to get dx. Dx is equal to dw divided by 3x squared plus 5. Now we have a small problem. We don't get a perfect cancellation. We have 3x squared plus 5 in the denominator and 60x squared plus 100 in the numerator. Can we do something so that a cancellation can subsequently be accomplished? So is there something we can do to the 60x squared plus 100 so that after we do that thing, we can fully cancel it with the 3x squared plus 5? And the answer is yes, there is something we can do. We can factor out a constant. So if I take 20 out, a common factor of 20 from that bracket, it looks weird, but it's okay. I'll have 3x squared plus 5. And then over here, I got dw over 3x squared plus 5. And now the 3x squared plus 5 top and bottom will cancel. So we have to do something slightly different this time. We have to do that factoring step to reveal the cancellation. Factor and cancel. So this 20 was a common factor. Okay, now we have 20 times the antiderivative of w to the 9. And this is an anti-power rule. So you have 20 times 1 over 10 w to the 10 plus c. So 2 times, and then w is x cubed plus 5x to the power of 10 plus c. And there's our answer. And I invite you to check to confirm that the derivative of this answer using the chain rule is what's originally inside the integral. Okay, it's another one, very similar structure to that. And we have one part of the expression, the 20x plus 10, that's inside a bracket. There's no power on that bracket. And we have another part of the expression, the 5x squared plus 5x, that's not in a bracket, but it's being plugged into an exponential function. So the part that's being plugged in to some operation, that's always going to be your first thing to try. So let w equal that thing. Let w equal that power. So w is 5x squared plus 5x. I'm going to rewrite the antiderivative. We have an antiderivative of that first term. We just have to hope it disappears. E to the w, and then dw. You have to replace the dx by something in terms of w. So I'm going to take the derivative of w, we get 10x plus 5. Rearrange, and dx is equal to dw divided by 10x plus 5. And this is just like the previous one. I can't directly cancel the 10x plus 5 with the 20x plus 10, but if we common factor a 2 out, we can cancel. So what I'm factoring out isn't the most I can factor out. I can factor a 10 out, but I'm looking at the cancellation that I want to have happen. So I'm going to common factor a 2 out, 10x plus 5 times e to the w times dw over 10x plus 5. So that the factoring is done to drive the cancellation. And a natural question that's asked is what happens if I factor and it doesn't cancel? Well, then it means that we have something else to do. It means that there's something wrong with our approach. So we're going to have to do some other manipulation. Like change that 20x plus 10 to a 20x plus 20, and it all falls apart. We're very much stuck in that case. We'd have to use a different approach. Okay, now we have a very nice antiderivative. We've transformed the complicated one in the x-axis to a simpler one in the w-axis. What do we take the antiderivative of in order to get e to the w? Well, we take the antiderivative of e to the w plus c. And then the last step, we can undo the substitution, let w become what it originally was, 5x squared plus 5x, and a lonely plus c. As before, as with the other problems, confirm that the derivative of that expression gives us back what's originally inside the integral. Okay. And one more before the break in the videos. We have 35 times the antiderivative of e to the 5x. Well, the first part is just a constant. Never substitute w equals the constant. It doesn't do anything. It breaks everything. But there's another part, the 5x, that's being plugged into the exponential function. So I'm going to let w equal 5x. I know ahead of time that I'm going to need dx in terms of w, so I'm going to take the derivative and rearrange it. And then that'll get plugged in. So I have integral 35 e to the w times dw over 5. 35 over 5 is 7, so 7 antiderivative of e to the w. Antiderivative of e to the w is once again e to the w plus c. And then I can replace w by 5x. Undo the substitution one more time. There you have it. And you can check the derivative of this. Derivative of 7e to the 5x plus c is going to be 7 times e to the 5x times w prime, so e to the 5x times 5 plus 0. And then we can multiply the 7 and the 5 together, so 35 e to the 5x, just like what the question originally had. We'll continue in the next video.